be rejected, right? If we have at home water filter, it passes clean water, rejects particles, unwanted particles, sand, etc. Right? We have signal processing filters that passes the wanted frequency and rejects the unwanted one. Right? So analog filters, when we say digital, again, analog word comes to our mind. Analog filters or classic filters are filters made of circuitry from hardware parts like capacitors, inductors, resistors, etc. Sorry. So if we have such a scenario and we want to change the filter specs, the filter specifications we have. For example, I have a filter, a low pass filter, for example, and I want to change it to high pass filter. I need to go to the circuit and remove some components, add other components, etc., isn't it? So we need to change the hardware in order to change the filter type or some specifications of the filter. Where digital ones, sorry, where the difference between the classic ones and the digital ones, digital filters circuit, digital filter circuit um, is a circuit like a microcontroller, a processor, etc., that has a program as well. So it is a board like Raspberry, like this Texas Instruments DSP processor, etc. And there is somewhere here a processor for a program. Okay, so if I want to change the specifications of the filter, I don't need to change the hardware. The hardware is fixed. I change just in the programming part. So I believe this is more reliable than uh, the classic ones, isn't it? Of course, more other advantages, but at the moment, let's talk about this. Do you understand, ladies and gentlemen? And of course, design is how to design this digital filter. Okay, now let's go to a blank slide. Let me allow me to open the lecture also from here so I can see your chat. And this class is 0304. Okay. Now, we have talked about this before. We said any LTI system or discrete time LTI system can be written in terms of ARMA process. Do you remember ARMA process, autoregressive moving average process? We said the output, let's say y of n, and I'll say there is a coefficient here, weighting coefficient A0 y of n, can be written as delayed versions of itself, A1 y of n minus 1, etc. Let's say up to certain an y of n minus n, sorry, minus capital N. this is equal to the output can be written as delayed versions of the output itself plus delayed versions of the input. I'll say B0 x of n plus B1 x of n minus 1, etc. up to, let's say, Bm x of n minus m. Isn't it? Do you understand this, ladies and gentlemen? Do you remember this? Okay. Now let's be more professional. Let's write this equation as a summation. So this can be written as this part, summation of a sub, let's say k, where k goes from 0 to capital N of y n, yn minus 0, yn minus 1, yn minus 2, etc., yn minus k. So 0, 1, 2, 3, 4, 5, 6 up to capital N, right? This is equal to summation of b, let's say L, from L0 to capital M of N there's a delay. Yes, now done. X of n minus L. So when I say I want to design a filter, it means I want to calculate h of n. I want to know what is h of n, the impulse response of the filter, or h of z, equivalently h of z. So how to find h of n or h of z? Who remembers? Who can tell us? Any idea? Y of z over x of z. Excellent. So let's find the z transform of this equation. We need to find the z transform of this equation first. So what is the z transform of this one? It is summation from 0 to capital N of a sub k capital Y of z, yn minus k, z transform is y of z, z to the power minus k. And this is equal to summation from L0 to capital M of BL capital X of Z, Z to the power minus L. And what I want is Y of Z over X of Z. So let's divide both sides by X of Z by X of Z. So here this is cancelled. What I want is Y of Z over X of Z. It is constant with respect to this summation K. So I can't take it outside the summation. So in this case, what is Y of Z over X of Z? H of Z, which is Y of Z over X of Z, right, is, let's write it the other page. It is this summation of BL, Z to the power minus L, over summation from K0 to capital N of A sub K z to the power minus k. Okay, ladies and gentlemen, clear? Okay, great. Let's now write this as a polynomial. Let's open this summation just to imagine what we have. I have b0 plus b1 z to the power minus 1 plus b2 z to the power minus 2 up to bm z to the power minus m. And same thing in the denominator, I have a0 z to the power 0 plus a1 z to the power minus 1 plus a2 z to the power minus 2 up to an z to the power minus n. Okay? Now, what we want again is h of n. I have h of z. If I have h of z, how to find h of n? I go to the tables. A reminder to everyone. I go to the tables. I look in the tables. Do I have the same function in the table? Yes. Done. No. Then I look. Do I have the same denominator in the table? Yes. Done. No. In that case, most probably we need partial fractions, right? We need partial fractions. So, we look here, we don't have the same function nor the same denominator, so we need partial fractions. How to partial fraction? We need to break the denominator into its coefficients, right? So we need to find what are the poles here. So how many poles do we have here? How many poles do we have? Why two? We have, look, if we have, depends on capital N exactly. So if we have 2 power 2 as the power of the denominator, in that case we will have 2. If the power is 3, how many poles? 3. If the power is n, the maximum power is n, we'll have n poles. N. So I'll assume that we have n poles, and these poles are, let's call them D1, D2, just let's give them some naming, Dn. Okay? Up to Dn. So in this case, if we would try to partial fraction this one, it will be, for example, something to the power minus 1 minus d1 z to the power minus 1, right? Plus b, for example, over 1 minus d2 z to the power minus 1 plus etc. up to 1, sorry, not 1, d1 minus dn z to the power minus 1, isn't it? Now here what we have in the numerators, we will have a, b, c, d, etc. So let's call them a1, a2, a3, a4 up to a sub n. But what we have done here, ladies and gentlemen, we have assumed that the degree of the numerator is less than the degree of the denominator. Because we don't know. We have the degree of the numerator as m and the degree of the denominator as n. I am assuming if the degree of the numerator is less than the degree of the denominator, I have this scenario. What if the degree of the numerator equals the degree of the denominator? What will happen? Any idea? If the degree of the numerator equals the degree of the denominator, we will have a constant k. Excellent. We'll have a constant k. So we'll have a constant k. Let's call it not k. Let's call it just, let's call it, for example, b. Just annotation. Now, look, ladies and gentlemen, one more time. If the degree of the numerator is less, we'll have this part. If they are equal, we will have b constant. What if the degree of the numerator, basically, all the time, we need the degree of the numerator to be less to partial fraction. Now, what if the degree of the numerator is 1 greater than the denominator? If they are equal, we will have b. If 1 equal greater, we will have z to the power minus 1 term, isn't it? So I'll have, let's call this, for example, b0, and this is b1, some constant multiplied by z to the power minus 1. It's usually, we use long division, if you remember. We use long division to find that. It's not a big deal to remember how to do that, but it's good to remember, I mean, the idea itself. What if the degree of the numerator is 2 greater than the denominator? We'll have one more term, which is b2 z to the power minus 2, isn't it? Until what? The maximum between them is the difference, which is bm, let's say minus n, z to the power minus m minus n. Okay? Clear? So it depends on the degree of the denominator and the numerator. Let's write this as summation, in summation form. So this is equal to, let me write it in the second page because I need to write underneath. Summation of b, I'll call it r, z to the power minus r, where r is from 0 up to capital M minus n. Look here, it's b sub r, z to the power minus r, from 0 to capital M minus n. And here, this one is, let's write it as summation from, let's say, k1, because d1, a1, a2, up to n, of a sub k over 1 minus dk z to the power minus 1. This is our system. This is our system in z domain. But again, remember, my target is h of n, is the impulse response, is the time domain. So what is h of n in this case? H of n can be found as, let's look at this one. What do we have here? Summation from 0 to capital M minus n of b sub r delta z to the power minus r inverse is delta n minus r, isn't it? This is pair number 4, if you remember. This is pair number 4. And this one, the other part, is summation from k1 up to capital N. Now this one, which pair is this one? 5 or 6? 5 or 6? could be 5 or 6 because we don't know is Z magnitude greater than dk. If it is greater, it is pair number 5. If it is less, it is pair number 6, right? So I'll assume it is greater. Why? I am assuming causal system. Well, causality is very important. So, ladies and gentlemen, I am assuming greater because causal is a good system. Causality is a good to be had in the system. But if you want in the exam to assume it is less, it's up to you. But you need to write to me. I am assuming it is less because I am assuming it's an uncausal system. You need to justify why. You want to use greater or less? You want to use pair number 5 or pair number 6? It's your call, it's your choice, but you need to show me that you are assuming it is greater or less. Clear? Okay. So in this case, if I assume greater, it's pair number 6, and pair number 5, sorry, and what we will have is a sub k constant dk to the power n u n. Clear? Do you have any questions so far? Okay, now look, let's go back to this equation. Now, what if we have the degree of the denominator greater than the degree of the numerator? In that case, this part does not exist, right? This part does not exist, isn't it? If the degree of the numerator is less, no part here. This one we don't have. Now, what if we don't have denominator? In other words, we just had yn without these parts. What will happen? We will have only this part, right? Isn't it? Because no denominator, no partial fractions. If we have the denominator and the numerator and the degree is greater, we'll have both. So basically, these two summations depend on our original system, the one we want to design. Do we have numerator only? Do we have numerator and denominator where the denominator degree is greater than the numerator degree, or is it less? So here in this part, so possibility of these three possibilities do exist. Now let's look at this part. If I try to draw this one, it's deltas, BR's deltas. So if I try to draw it, it's something like this, whatever the values are, right? How many samples do I have here? How many samples do we have? We have from 0, R0, until capital M minus N. So how many samples? M minus N plus 1. From 0 to M minus N is M minus N plus 1. Right? So I don't care. Is it M? Is it M minus N? Is it M minus N plus 1? Just to be precise. So what I do care about is this system has impulse response, or h of n, that has a finite length. So how many samples I have? M minus N plus 1 samples. It could be 100, 1 million, 10 millions. I don't care. The most important thing is the finite impulse response. The impulse response here is finite. Okay? Clear? Well, in the second one, I have UN. So, and if you remember, UN is a function that goes up to infinity, right? So what do we have here? We have infinite impulse response. The number of samples in this function are infinity. So we call this, we abbreviate it as IIR system, infinite impulse response system, where the previous one we abbreviate it as FIR or FIR systems. FIR system, okay? Clear? So two main classes of systems or filters, FIR ones and IIR ones. Now, actually we are supposed to explain both of them, but due to some lack of time, we will be just highlighting the most important one. We will just be discussing the most important one, which is IIR1, which is IIR1. Okay, so we'll be explaining this. We'll be more interested in this one. So let's go back to our slides first. So this is what we have done. I explained this. I derived it in detail. This is the two classes, FIR. This is FIR, and this is IIR. So we'll be learning, ladies and gentlemen, how to design a digital IIR filter. A digital IIR filter. This is the one of our interest. Now, this is just a very simple example. We don't need this one. Let's look at this figure. Who remembers which filter is this? Which filter is this one? This is a low pass filter, right? This is a low pass filter. And this one is a high pass filter. Of course, ladies and gentlemen, I wish everyone remembers that this is the DTFT. And we said when we talk about DTFT, it is periodic with period 2 pi. So this is something that keeps repeating itself from minus infinity to infinity every 2 pi. So can anybody tell us a general note about these two, low pass and high pass, a relation? Can you relate these two in a way? Can you look and think of a way to relate these two functions, magnitude responses? They are actually complementing each other. In other words, I have 0 here where it's 1 there, right? I have 1 here where it is 0 there. So mathematically speaking, how to find a relation mathematically between low pass and high pass? Low pass filter is 1 minus high pass, right? Or high pass filter is 1 minus low pass, right? So h of high pass of j omega is 1 minus h of low pass of j omega. We usually don't write 1. We call this one all pass. It's all pass filter. When I say all pass, it means 1. I mean for the whole period it's 1. Okay, clear? So basically, ladies and gentlemen, what I want from this one to tell you this: if The question is design a low pass filter, and I know how to design a low pass filter. It's done. If the question is design a high pass filter, and I know how to design a low pass filter, in that case, I just design a low pass filter, and then one or all pass minus low pass. As the last step, I get the high pass one, right? Do you understand the idea? I don't need to repeat everything from the beginning. So, because they are totally two different filters, I don't want to waste time in teaching or learning how to design this one and this one different ways. So we can learn just low pass, and then if I want a high pass, one minus low pass, I get the high pass. Done. Is this clear? Okay, great. Very good. Sorry. And this one, band pass, what is the relation between band pass and low pass? It is just a time shift, right? If you shift, sorry, a frequency shift. It's shifting in the frequency domain. If you shift this to the right, because we have two, one here and one there, and one here, and more. If you shift these two to the right, like if this axis comes here, you will have this one, isn't it? Or if you shift it to the left, you will have it this one, right? So no need again to learn the band pass one. This is band pass filter. I just, if I know the low pass, I can shift it to get the band pass one. And this filter is band stop, as we explained before. It's a complement of band pass. 1 minus band pass, 1 minus band pass, you will get this one like this, right? Again, I design a low pass, shift 1 minus to get band stop. Is this clear, ladies and gentlemen? Okay, very good. So our target in this course will be learning how to design a digital IIR low pass filter. So what we are going to do is to design a digital IIR low pass filter. Okay, clear? Now let's try to draw how this filter looks like, the magnitude response. The magnitude filter response of the low pass filter is usually as we have shown a moment ago. I'll just draw it at a larger scale. This is, sorry, pi, and this is omega c cutoff frequency, right? And this is, for example, if we assume normalized one is 1. And as we said before, we just draw the right side, and we know that the left side is a mirror of what we have on the right. Now, in this one, what we have here is an ideal low pass filter, where in reality, in real life, as we said before, nothing is ideal. So in reality, the filter does not look like this. In reality, the magnitude response looks like this. So this thing, let's define some important points here. So the orange one does not exist in real life. What exists in real life is the green one. Now, look, in this region is the region where any frequency is in this region, it will pass. So we call this pass band. This is the pass band. Any frequency in this region will pass. Clear? This region, any frequency in here will be not passed, will be stopped. So we call this stop band. Stop band. This is pass band, this is stop band. In between here, this region is the region where we move from pass band to stop band, right? Where we transit from pass band to stop band. So this is transition region or transition band. Clear? Do you understand, ladies and gentlemen, these namings? Okay, great. Now here, this region, as we said, is the pass band. So I'll call the frequency here is W or omega P. Omega P is the pass band edge frequency. Pass band edge frequency. And this frequency, I'll call it omega S. It is the stop band edge frequency. Stop band edge frequency. And this here, this value, I'll call this point delta S. It is the peak value of the stop band region. Peak value, delta S, sorry, is the peak of the stop band, or we call this shape is lobes. They are at the side, so we call these side lobes. Is the peak value of the side lobes. Okay, clear? Now this one in the middle, and there is rippling here. It ripples around 1. So I'll call this value, if this is symmetric, so I'll call this 1 plus delta P, and this is 1 minus delta P. The pass band ripple value. So delta P is the peak of the ripple of the main lobe ripples. Main lobe ripples. Okay, clear? So what we need to do, ladies and gentlemen, in reality, I say I want to design a filter that its ripples are between this value and this value, whatever, and its edge frequency is omega P and omega S. I say what is the values, and delta S should be somewhere here. And accordingly design your filter. Accordingly design your filter to get something like this, for example. Clear? So this is our target. I put my constraints. I put what is the value of my omega P, what is the value of my omega S, what is the value of delta P, what is the value of delta S, and accordingly I design my filter. This process to be done, this process to be done, I need to design the filter first in continuous time, and then um, make it digital. So I start with analog filter, and there are many methods to design analog filters. Like one of the most famous techniques is called Butterworth filters. Have you heard about Butterworth filters? This is the one I explained a moment ago. So Butterworth filter, it's okay. There are Chebyshev, Butterworth filters, etc. So we will discuss Butterworth filter, how to use, and then this is analog. I will make this digital through many techniques. There are many techniques to convert from analog to digital in frequency domain. Um, one of these main or two main techniques of our interest in this course, one of them is called impulse invariance technique or impulse invariance method, and the other one is bilinear transform method. So we have two main techniques, impulse invariance technique and bilinear transform technique. These are very important. Well, the right thing is not does not appear here. I will fix it inshallah. So these are two main techniques, very important for us. And trust me, in the final assessment, you will have at least one question about one of these techniques. So we need to understand this very, very well, inshallah, after the Eid holiday. Okay? Clear? Okay, great. So please, now ladies and gentlemen, the most difficult part in here is learning how to solve a system of nonlinear equations. So if possible, please make sure you have your calculator with you um, next time, please, okay? So please don't forget your calculator. Okay. Now, ladies and gentlemen, do you have any question before because I have things to talk about regarding the course project and many other things. And the assignment, I will talk about it, Tifla, as well. Okay, so now let's start by the course project. Now, course project, next week, as per our plan, we have to demonstrate our prototype, right? Prototype demonstration is planned next week. Now, I don't want you to come Monday or Tuesday demonstrating. So I will, first of all, I will shift this to week 13. So demonstration is week 13. Okay, clear? Is this clear, ladies and gentlemen? Okay. Now, again, I received many questions. I will send the email of these. I received many questions like prototype. Do we have to do hardware or just software? Now, ladies and gentlemen, when I say prototype, it means a system that has input, gives you output. This system could be a hardware, it could be a program, and you give the program a certain input, you get a certain output. It could be hardware. It doesn't matter, is it hardware or it's just a program? Do we understand? Now, what I need from every group of you, you need to finalize your prototype. Again, between quotations, your prototype, the hardware or the uh, code 1 and run the system, show me the output and the input, and take a video of this thing. You need to take a video of the whole process. This is very important. Look, ladies and gentlemen, please do this in a professional way, in a nice way. Not very professional, of course, but in a nice way to show us. It's a show thing. And you will be evaluated. You will be like 10% evaluated of this demonstration part. Of course, there are some questions and answers, but you need to we need to evaluate you here. So please do your demonstration part as best as you can. Take a video of this. You need to share with us the link of your video. You can put it on OneDrive. I can create a link on Moodle to submit. Or if you don't, or if you cannot take a video, in that case you need to open your camera live during the class and show us in front of the camera. It's just 2-3 minutes, Ya Nasser, not more than 2-3 minutes. Clear? Okay, now do we have any question regarding the project prototyping or demonstration? Yes, you need to talk in this video. You need to explaining. You either explain in the video, or you just show the video here and explain over the in the class, in front of the class. It's up to you. Just you have a system. You need to tell me what is your system. I need to, when I see, I listen, I understand what you are doing. I said yes, it's okay. Yes, yes, in week 13 during the class. Before the class, one maybe hour before the class, you send me the link, and that's it, or the video itself. Why pictures, ya Ghanima? I need the system is running. I need live video. System is running. Um, Coding. Why do you take pictures and record voice over that? It should be a video. No report. I will shift it. I will shift the report. Don't worry. I need. Look, ladies and gentlemen. I told you this before. I don't want to squeeze you, to punish you. I need to help you. So I will. If you feel you can submit the report week 13, it's fine. If not, I will shift it to week 14. I said you can explain the video in the class. Yes, ya Mariam. Okay. Do you have any question about this prototype? Okay, I think no. No, no, no. As long as the theme is one of the themes in our syllabus, no need, Ya Nasser. Where is that, Ya Fajr, in the email? Where is that, Fajr? No need for the block diagram. No need for the block diagram. Yeah. In the demonstration, just show me the code running, taking input camera, taking a picture, and then giving you output, or a robot running, or whatever you have done. Live demonstration for that, running the code, and that's it. No need for block diagram in the demonstration part. In the final report, now no need. In the demonstration, no need to submit the code. In the final report, you will submit the code. Okay, Mariam? Okay. Now, I had one more question about the in-class assignment. Um, Now, ladies and gentlemen, before we used to have some students, let's not call it cheating, but what they are doing is, I have a problem in one question, I ask my friend, he helps me, he gives me the solution. I ask somebody else, he gives me solution, he helps me, etc. And that's it, done. I had before one case, two cases, three cases like this in every class. But having 30, 40 cases in one class, this is a big, big, big issue. Now, I know all of you do care about grades. Even trust me, the grade at this level does not change that your GPA that much. And trust me, if you were in need of some grade and you talk to me honestly about that, I would help you rather than cheating. I'm sorry to say the word cheating because it is really cheating. And you know that as engineers, this is against our code of ethics. This is against our um, values as Muslims as well, because this is sin. Cheating is a sin. It's haram in Islam as well. So I cannot imagine how this happened. It's not only cheating. Unfortunately, blindly cheating. This is so bad. Blindly cheating is so bad. Look, I will just give you something. 1/4. 1/4, okay? This is the number 1/4. Maryam al Rashid. By the way, it's not Maryam nor maybe not in your class actually, but just giving names from the list. Maryam wrote it 1/4. Then Fajr came and wrote this 1/4. Instead of 1/4, she wrote 0.25. Okay? 0.25. Then Muhammad Salman came, he's copying from Fajr, and instead of 0.25, he wrote it's 0.25, but he wrote it like 0.25 like this. Then Nasser is coming to cheat from Muhammad Salman. He didn't see that this is 0 or 6, so he wrote it 6.25. And everyone else after then wrote this as 6.25. What's this? From where this 6.25 comes? And at the end, I don't know how it goes back to 1/4. How it goes back to 1/4. Come on. If you want to cheat, you don't have 5 minutes to read what you are cheating? Come on. How comes? This is totally not accepted. This is totally not acceptable. This is serious, Ya Nasser. Really, this is very, very serious. This is very serious. Now look, ladies and gentlemen, it happened to me one before. It happened to me one before. Um, it was a question last semester. No, no, not last semester. This semester actually, in one of the assessments in another section. Um, it is like he's writing a number. I don't know what. Let's say something less than infinity. I think one less than infinity, and one, etc. Something like this. Something like this. One. He then puts just. It should be like this. One less than infinity. So etc. Now one student wrote like this. One less than infinity. Then he put comma. One, so something like this. It's okay, fine. Then another student came and then said one less than. Well, what is this? This is 8, but he wrote it wrong because he wrote it 1 8.1, 8 comma 1. So the other one came 1 less than 8.1, and from this point they started all writing it as 8.1. Look, it's 1 less than infinity. It came as 1 less than 8.1. From where did you get this 8.1? This is terrible, ladies and gentlemen. This is terrible. It's up to you to do this or not. But trust me, no tolerance at this point. No tolerance at all. I am here from the beginning of the semester. I'm saying I am helping everyone. I want to help everyone. But behaving in this way, and by the way, I'm not talking to your class. I don't think that this message is to your class. This message, I also delivered this message to yesterday's classes. This message is to all Spring 2021 DSP students. I know some of you or many of you are trying their best, are trying their own solutions, are doing very well, but I hope everyone will do the same thing, will behave the same way. Now this is, I already finished grading the in-class assignment. I cannot post it right now until we find a solution about this. I need to find a solution about this thing, similarity issue. To be frank with you, clear? Am I clear? Yeah. Who asked about the in-class assignment at the beginning of the class? I think I don't remember. Maybe Tifla. I think Tifla. I think. Okay. So I'm sorry for that. Bear with me, please. I cannot show the grades right now, but hopefully by today it will be sorted out, and after then I will announce the grades. Okay, ladies and gentlemen, thank you very much. I'm sorry I kept you waiting a little bit more. Thank you very much. We will talk about صفح and عفو إن شاء الله after the grades يا طفلة. الله اللي يصفح عن الجميع، الله يصفح عنا أجمعين إن شاء الله يا رب. I wish you happy Eid holiday. Enjoy your Eid without gatherings. Please avoid gatherings as much as you can. Take care of yourselves and see you inshallah next week.